Hello and welcome back to Calculus 3 for one last time. Yeah, that's it. Green's theorem, and you just need to show off your skills tomorrow. You're done. The homework will remain open till midnight tomorrow. So technically, when you are done with the class, you can still do stuff. If you become nostalgic right after you walk out of classroom. All right, if it hits you, I will never take Calc 3 again. Unless you severely messed up the final, in which case, summer 2, 10:30, we go from scratch, right?
Is it not fixed yet?
What happened?
Full, summer 2?
Yeah, it's full, but
You can show up, I'm sure.
bring in the lawn chair. Put it there.
They're going to go.
Yeah, you can totally white trash that class. Anyway, the Green's theorem. As I mentioned yesterday, both of these sections on conservative vector fields and the Green's theorem are going to be one of those quality of life kind of lectures where you figure out that in certain situations there is an easier way to compute the line integral than the standard long way we learned in chapter 14.2. So the Green's theorem has it has two flavors. We'll see both of those, and yes, and it's going to be applicable only in certain situations. So you need to know that situation and then work in those parameters. So let's immediately write the theorem and then start solving. So again, no new concepts here. It's just a different way to do certain types of problems. So guys, the most important part, apart from the formula itself, is are conditions under which the formula applies. So it's the same like applying for a scholarship. If the scholarship says if your GPA is above 3.8, you can apply. Well, clearly, if your GPA is 3.7, you can't apply because the condition did not apply to you. So make sure that the conditions from the theorem apply first, and then you can go on and unleash the formula. Otherwise, if the conditions do not apply and you unleash the formula, you are going to get a number that it's wrong answer, right? So, what? Yeah, you're going to get 7, right? And then, yeah.
I'm still waiting for us to get a question where the answer is 7. I'm expecting one of the
Yeah, it doesn't happen. So let curve C be simple, closed, piecewise curve oriented counterclockwise. So this is all just about the curve C. Now, that encloses the connected and simply connected region R. You remember all those 8 pictures from yesterday? They're all in here. So that encloses simply, connected and simply connected. So connected.
He closes.
Yeah. Toss in an N there, it's fine. And simply connected. Region R. In the plane. So, assume that the vector field given by standard FG, where F and G have continuous first partial derivatives. Does anyone notice just in this statement that they're all 4 chapters playing the role in here? We haven't even gotten to the formula yet in our then, and here's the crazy statement, the line integral with a circle around the integration symbol of f dr is the integral with a circle, I'll explain that soon, of f dx plus g dy is equal to double integral over the region R of the dg dx of partial g partial x minus partial f partial y dA. Whoa. I don't even know where to begin. I do know where to begin. So, what is the statement? Well, if you are connecting this to your original statement for the line integral, we are technically saying that this is equal to that under these circumstances, right? That's that. This statement is really interesting, in my humble opinion, because on this side you have a single, on the other side you have a double integral, and they're somehow equal. They both have stuff inside, right? So dimensionally that might, but it actually does, because if you know derivatives, and that essentially cancels one of the integrals, so dimensionally we're good, right? So that's the first obstacle. Second thing is, let's discuss this and then that. Why is there a lag? I'm already, there we go.
Yeah, it crashed for a second.
So if you are looking at the regular integral that you know and love for years, and then you see this integral now with this circle around it, it's just a fancy notation that actually helps us see that a region is enclosed, and the curve C, which is in the index here, is actually closed, smooth, and all of the parameters from the text above. So this line, this circle around the integral symbol, is just signifying a whole bunch of these things that we went through in the text.
Is that why for like the Gaussian circuit they use that integral because it's in a closed?
Yes, yes.
Okay.
Now, looking at the conditions for this for the Green's theorem to work, if you have a line like this, which is C, clearly this formula doesn't apply. Can you compute it? Yes, and the answer you get is going to be garbage, because the condition is requiring closed curve. So you have to have a closed curve. It has to be smooth, which means differentiable. It has to be oriented counterclockwise, and then it has to enclose the region. So you can talk about a square, that's fine. You can talk about a quarter circle. You can talk about half circle. You can talk about the entire circle. You can talk about the triangle. I don't care what it is. They can have edges, because over here, guys, it says piecewise smooth. Piecewise smooth means it's differentiable, and it's allowed, the corners are allowed. When you have a spike in a function, like you have an absolute value of x, n is not differentiable, because you have two competing slopes. There is a negative one slope coming from the left and a positive one slope coming from the right, competing for the right at 0, right? And then you can't have any of them win, because you can't have a favorite child, which is not true, but yeah. Anyway, yeah, all of you have siblings, and they're either better or worse than you. All right? Yeah. Yeah, unless if you're a single child, in which case you're best by default. Anyway. Huh?
And worse by default.
Does this mean you have a favorite child?
Of course.
Oh, God.
Anyway. So these are all closed curves, and they are all okay for our case. Now, what's important is to have the counterclockwise parametrization. And if you remember when we did the parametrization for our, so there's the counterclockwise parametrization on all of these. And if you remember when we transformed the regions in 13.7, when we did all of the parametrization for each one of the lines, yeah, that's back. All right. Now, the last part is, well, we actually don't have to parametricize things here. Yay! Because observe what you are setting up. You are setting up a basic double integral, which could be 13.1, 13.2, or 13.3, right? Because it's either rectangular regions, general regions, or a polar integral, right? We are not going into triple integrals with this theorem. Sections later on in Calc 3, because there are other 4 sections that we unfortunately didn't get to, they deal with the triple integrals and this kind of stuff. So this is only the double integral stuff set up. And if you see what you have in here, the vector field, right, will govern the guts of the integral, and your geometry of the problem will govern the limits of the double integral. So if I say that you are on a semicircle, you might want to deal with the polar coordinates. If I say that you are on a square, well, or a rectangle, definitely rectangular. If you have a parabola or something like that, well, then general regions will do. So the idea of these problems is to skip the one-page calculation of the line integrals, where you have to do parametrization and all of those dot products and all of that kind of stuff that takes forever, and very simply plug some partial derivatives which are readily available from the vector field which is given to you, and then also the geometry of the curve C, which is also given to you, will provide the limits for your integral. So let's immediately take a look at the example. Oh, and by the way, here is also part of the definition or the theorem. The dg over dx minus df over dy is called the curl of the vector field f. So so is called curl of vector field f, which is your fg, right? So the problem on the final exam could say compute the curl of, and then I give you vector field. You just need to compute the difference of two partial derivatives, and then that's that. Now the other part of this theorem is that if the curl is 0, the field is called irrotational. All right. So if curl is 0, f vector field f is called irrotational. Not irritating. Not irritating, irrotational. Right. All right, great. So let's take a look at an example of this, and then try and figure out all of these things. Let's jump into homework. You can read the examples, right, because you know all the letters and things. Just gonna do some extra stuff, right? I heard that so many times. Yeah, on the farm. Okay, so let's start off with the vanilla example, number 12, where the vector field is given as xy. By now you should be able to recognize, no, sorry, it's yx. Never mind. And we are on the square. I'm just going to say unit square. So unit square is 0, 1, 1, 1, and 1, right? That's the the unit square. All right, so we are on the unit square. It's very quick to compute this. We are looking at the square. We know, so it's connected. The curve C, which is the black line which outlines the square, is closed. All of these are linear straight lines, which means they are differentiable. I know it has corners counterclockwise, so there's that piece. So all of the conditions for us to use the Green's theorem, rather than to do all the parametrization and stuff, are met. So we can calculate the line integral, f dr, as the double integral of the curl, and then we have dA. So now region R. Well, we have a square. What could be easier than that? Technically nothing, right? So we have this to be, since it's a square, is 0 to 1 and 0 to 1, whether you want dx or dy. Remember that over there I said you can swap the order of integration if it's a rectangular integral, right? And then you have your curl that you have to compute. So now partial g partial x, well, partial g partial x, that's 1. And then partial f partial y is going to be also 1. And we are calculating this at 0, right? Which will give us 0, and we just found the irrotational vector field, right? The curl was 0, so it's irrotational vector field, and we found that it worked out to be 0. Nice.
So what is that? It's irrotational.
There's no this. For the vector field, it means it's a radial field is irrotational, right? Because it radiates straight out. It doesn't spin the vectors into like what's rotational? Your tornado is rotational. Your tornado. A tornado is rotational, right? Good. Well, I hope that wasn't hard. I meant flux version of Green's theorem. There you go. Does this make it better? No, you just made it worse. You ruined it for everyone. And now you'll have to live with that.
I can do that quite easily. But, thanks.
So we know that there is circulation and the flux when we talked about the line integrals which involve the vector fields, right? So now we need to have circulation and the flux version for the Green's theorem, right? So now if you go back to your section, by the way, it has the same. So this is the definition. Same conditions. There we go. And then we jump immediately into the formula. And the formula says that the closed curve, right, C integral of f dot n ds, this is your standard setup for those, which was given as, what was that, f dy, right? minus g dx is now going to be, again, the double integral over region R of df dx plus dg dy dA. And that would be the flux version of the Green's theorem. Now, together with this, we have this df dx plus dg dy is called divergence of vector field. Good effort. Vector field F. So that's called the divergence of vector. And then also, if divergence is equal to 0, we say vector field F is source free. Now, I'm always fascinated of how easy it is to understand this concept if you have the right images, but then again, I'm highly visual. So this will help some of you, and others will still go, oh, what the hell is going on? When I draw a radial field, which is two-dimensional, looks like this, three-dimensional is the sun, I am thinking of radiating some energy out of it. So a sun is a good example of a radial, three-dimensional radial field. Explosion of a grenade or something is also radial because it has a source, the origin, and then it disperses in all directions, right, around it. So any type of behavior like that where energy or particles are emitted away from the source is called radial. And now the forces of particles, if you're thinking of a grenade exploding or the whatever, right, you have the little particles that are projected, right? The force that pushes that particle is actually a vector field, right? There's actually a whole branch of mathematics called mathematics of detonation that it's actually used for these kind of things. All of the defense stuff and everything is actually first mathematics, then the engineering and development, and then actually the things exist. So if you are looking at the radial field, and I'm drawing the 2D case, observe that you know what the divergence means, right? The two things are going away from each other. If you are to calculate the distance between any of these two, you see that the distance is getting longer and longer between them as they are going further out, right? So they diverge. So it's somehow, to me, all of these concepts, right, when you look at the picture and you look at the naming convention, right, you see that, okay, so divergence is two things going apart, because it's clear that if I extend this ray up to here and I extend this ray up to there, this distance here is much longer than the distance I have there, right, when these two rays were closer, right? I mean, when both rays are shorter. So when I say that divergence is 0, if divergence is 0, we say that the vector field is source free. Well, only if you have a source, you have the divergence, right? It's like a gossip, all right? So it spreads, right? If I have a source, someone comes up with certain gossip, like I am great, then two pieces of information, right, will eventually diverge because it's make-believe, right? We have all the fake news today, so that's technically what it is, right? And nothing supports anything else. So if divergence is not happening, i.e. divergence is 0, then there is no source. Does that make sense? In order for divergence to happen, you have to have source, which is the starting point for everything to diverge. In a rotational field, which has no source, there is also no divergence. Right? Right. So you know, these concepts, I mean, yeah, I understand this is a short course because it's only, you know, it's a summer course and so on. Everything is crammed and you have to, you know, deal with hours of this stuff every day. But, you know, once the course is over, those of you interested in this, especially if you're mechanical and electrical engineers, you will have to think about these concepts and try to relate the concept and the wording used and then associated pictures to make sense out of these things. So the questions might be calculate divergence, calculate curl, or then use the Green's theorem to compute, right? Because your final exam does have Green's theorem as a learning outcome on its own, which is, you know, a little bit funny because it's a single lecture out of 20 plus lectures we had. It's singled out, but as a learning outcome, and then you have another 3. So technically you should get like a 25% of your grade, right, on that one question, right, because it's 25% of your learning outcomes. But then, no. There you go, two-dimensional divergence, and I don't even know if I should do the example for this because I believe that you guys are able to take two partial derivatives and add them. Let's do one. You are welcome. You can leave your thank you cards and cakes. No. I was thinking at the storage unit, but that's fine. You have the storage unit? You won't believe. I received multiple cakes. There's a reason why I'm like this. Anyway. So vector field is y and a negative 3x and R is a region bounded by y equals 4 minus x squared and y equals to 0. So those are the bounds. Well, the first order of business for me when I solve these is to first graph the region so that I can do that first. So I can quickly set the double integral later. I know that this is going to be a downward opening parabola going through 4 and negative 2 and 2. And I also have y equal to 0. So this is my, the green line is the there we go, green line, and this green line we can going that way, right, to be counterclockwise. I do have 2 spikes, but again we don't care about those 2 spikes because it needs to be piecewise smooth, and it is, right. I don't have a spike between like on any of the lines. I have spikes in the corner when 2 different equations connect, so that's okay. So I have the image, right, which is good enough for me to set up the integral. Hopefully you see that the only version of the integral that you can do is going to be dy dx, because you must have dx in charge. In this case, you must have dx in charge because dy would fold onto itself, and then you wouldn't be able to do the problem. Also, we know that f is what I need to do now is to compute the divergence and plug that into, right? So partial f partial x is 0. Yeah, it's a flux. Anyway, so now we have the double integral, and to get my I mean it's 0 over here, so yeah, but when you have the upper, right, it's going to be dy dx. So x is going from -2 to 2. Please remember not to cut the symmetry and all that kind of stuff. And the other one is going 0 to 0 to what? 4 minus x squared, yes. Source free. So quickly compute some of these. They are very quick. You either know what you're doing, you know the formula, or you don't. And remember what I said at day 1. Calculus 3 is learning these formulas because all of your integration is Calc 1, right? Have we ever done partial fraction decomposition? No. Have we ever done by parts? Once, that I remember. And we never did trig integrals. We never did, right? So really, all of your integration and all of your derivatives, so all of the calculations are, you learning Calc 3 is learning the formulas and learning the concepts. So no formula sheet for anything. So this is it, right? Let's just, let's restart the stream after the break for the final exam review. We can do some problems and yeah. Calc 3 is officially over.